Hello, I'm Edmund Storms, and I'm here in my office in Santa Fe, New Mexico on a cool day in December 2007. I would like to tell you about cold fusion. Cold fusion is the most important and underappreciated discovery of this century. In fact, this discovery has the potential to change the lives of everyone on this planet and provide clean, cheap energy for the foreseeable future. Well, now that I have your attention, I'd like to justify this statement during the next 50 minutes. But first I need to explain the meaning of the term cold fusion. This term was applied to the discovery made by Professors Fleischmann and Pons in 1989. Here you can see the pair holding one of their cold fusion cells when they were much younger and ignorant of the events they would suffer. Growing understanding makes cold fusion a very inadequate way to describe the process. Nevertheless, I will use the term because it is a name that most people associate with the discovery. Presently, several other names are also applied. This phenomena called cold fusion is the popular name. Low energy nuclear reaction, LENR, is now the general description. I like to use the term chemically assisted nuclear reaction because it better describes the environment in which the phenomenon occurs, and this is CANR. At the present time, condensed matter nuclear science is the name of the field of study. That's CMNS. The idea of cold fusion creates a mixed reaction in people. Non-technical people, when they learn about the phenomena, recognize it as a possible ideal energy source. The process makes energy without producing radioactive products or carbon dioxide, and it uses deuterium, which is not radioactive and is plentiful in all water. In addition, the process is simple and can be easily made to occur on a small scale for local use. These features make the process very attractive, especially in view of the need to stop adding carbon dioxide to the atmosphere and to stop accumulating dangerous radioactive material from the fission reactor process. In contrast, most scientists who know about the claims think they are nonsense for various reasons. The effect has been difficult to produce. Such a fusion reaction is believed to be impossible at such low energy, and the theories that have been proposed to explain the results are filled with unacceptable assumptions. Many less rational reasons are also used, but I won't go into these just now. Even if cold fusion is unlikely to be real, the collection of growing problems such as global warming, the need to desalinate seawater for irrigation and domestic use, and the increasing cost of oil and uranium should be enough to encourage studies to see if the skeptics are correct or not. Work is being done in a number of countries: Japan, Italy, Russia, the Ukraine, Israel, United States, China, and France. Most of the work and developing understanding is now taking place in Japan and in Israel. So, we have an interesting situation. We have an energy source that, if real, can solve some important problems we now are facing. On the other hand, many people who are in a position to support development of this source of energy think the claims are based on bad science. My goal today is to show you that cold fusion is a real phenomena, and it has the potential to be the energy of the future. Forgive me if you already believe that cold fusion is real and just want to learn what is presently known. I will provide such information as I go along, and so you won't be disappointed. Before starting, we need to understand exactly what cold fusion claims to do. When deuterium fuses with itself or with other elements, a lot of energy is released. A couple of fluid ounces of liquid deuterium would provide all the energy a person would need to support the standard of living existing in advanced countries, including transportation, for a lifetime. The amount of energy available is much greater than from uranium and the fission process. Now, these reactions can take various paths. The fusion reaction can take three paths. The first forms helium-3 and a neutron. The second forms a proton and a triton. These two paths take place at high energy in plasma and a hot fusion reactor. They occur more or less in equal amounts. In contrast, the cold fusion process results in helium-4, but no gamma. So you can see that the environment plays a big role in the paths that the reaction takes. In addition, at low energy, another reaction takes place where a number of deuterons combine to enter the nucleus of a heavier element to produce what would be a fusion reaction, and this may or may not be followed by fission of this more heavier element. This reaction is called transmutation. Not detected is the fusion between a deuteron and a triton, producing a neutron, and the fusion between a deuteron and a proton, forming helium-3. As you notice, the path changes as the conditions change. This fact is very important, and it means that failure to see a behavior observed at high energy cannot be used to show that fusion is not occurring at lower energies, typical of the cold fusion environment. Normally, neutrons and gamma radiation are not detected outside of the apparatus. This lack of expected radiation is one of the reasons the whole idea is rejected by some people. For them, no neutrons mean no fusion. On the other hand, this gift of nature is very welcomed by people like me who study the process, and it should be welcomed by people who may make use of the generated power in the future. The absence of dangerous products and the simplicity of the equipment needed to cause the fusion reaction makes the method attractive as a source of energy for each house. Space heating would simply use the generated heat. Direct conversion of heat to electricity without moving parts could be done using thermoelectric converters. This could supply electric power for domestic use and personal transportation using plug-in hybrids. This is only a small fraction of the advantages such a source of energy would provide. In contrast to cold fusion, a hot fusion program called ITER now is underway in France. The hot fusion process requires the use of a very large device, heat generator, energy generator. You can see the size by comparing it to an ordinary person. The fusion reaction occurs in this space, which is surrounded by very intense magnetic fields to keep the hot plasma away from the walls of the apparatus. This generates a large number of neutrons, which are then captured outside of the apparatus to convert the neutron energy into tritium, which is then fed back into the machine to institute further fusion reaction. Now, tritium should not be produced under these conditions, so this is very unusual. Other elements are produced that were not present in the apparatus initially, and these frequently have abnormal isotopic ratios. Finally, various consistent patterns of behavior are found. That is, when conditions are changed, the same behavior is seen as a result, no matter who runs the experiment or makes the observation. And finally, energetic particle and gamma emission is seen if these are detected. Efforts are made to detect these within the apparatus. They're not seen outside the apparatus. I don't have time to go into that evidence in detail, but nevertheless, the energetic particles and emissions are seen. Cold fusion can be initiated a number of different ways. The most thoroughly studied, and the one that Pons and Fleischmann used initially, was electrolysis. Electrolysis consists of passing a current through heavy water containing a little bit of lithium salt. This decomposes at the cathode, which is palladium, and eventually a nuclear reaction occurs at the cathode material. A different technique has been discovered recently where the nuclear active material is simply exposed to deuterium gas at sufficient pressure and with a little applied heat sometimes. Just simply exposing the nuclear active material to the gas generates heat and nuclear products, and we'll talk about that in more detail. A liquid plasma can be formed within the electrolyte in an electrolytic cell simply by applying a high enough voltage to the cell. a voltage in excess of 100 volts is usually required to generate and break down the liquid into a plasma. This applies a lot of energy and high temperature to the environment and results in a more rapid nuclear reaction at the cathode, which frequently is tungsten. A gas plasma can be formed between two electrodes. If this plasma is formed in deuterium, and the electrodes, it turns out, can be many different things, but nevertheless, a nuclear reaction is found to occur at the cathode surface. Proton conductors are complex oxides that can dissolve deuterons or protons, and when a voltage is placed across them and they're heated, the protons or deuteron are caused to move, and in the process, heat and nuclear products are formed. Sonic implantation involves applying ultrasonic frequency to a liquid, usually heavy water, and this causes the bubbles that are formed to collapse on a metal surface. And when this happens, the contents of the bubble, as they collapse, are injected into the metal. Gradually, the concentration of deuterium and oxygen build up in that metal surface, and a nuclear reaction is initiated. This is different than sonofusion, which is an attempt to create hot fusion within the bubble itself as it collapses. And finally, if laser light is applied to a material at high enough intensity, various nuclear reactions can be made to occur. Well, before we talk about heat production, we need to understand how heat is measured. It's measuring using a calorimeter. Various kinds of calorimeters have been used successfully to measure heat by the cold fusion process. And we'll go through the four of them just to show you how they work. The single-wall isoparabolic calorimeter was the one that was used by Pons and Fleischmann initially, and it's the most simple of the four. It consists of measuring the temperature within the electrolyte, within the electrolytic cell, and measuring the temperature outside of the cell to get the temperature drop across the cell wall, which is proportional to the heat flow. The outside temperature is easy to measure because the cell is usually in a constant temperature bath. The problem comes in measuring the temperature inside the cell. Because heat is being generated within this liquid by electrolytic action and hopefully by a cold fusion reaction, convection currents are formed, and these cause temperature gradients to occur. Therefore, it's difficult to know precisely what the average temperature in this liquid is. Pons and Fleischmann got around this problem by clever design. Other people have stirred this liquid to eliminate or at least reduce the temperature gradients. Nevertheless, this is a problem that can be solved by using a second wall or a double wall isoparabolic calorimeter. Here, a wall outside of the electrolytic cell is used to measure the heat flow by measuring the temperature on the inside of that wall and again on the outside of the wall. The temperature difference across the wall then is a measure of heat flow through this material. And you'll notice that the temperatures are now independent of what's occurring within the cell itself. A Seebeck calorimeter is similar to an isoparabolic calorimeter in the sense that this wall contains hundreds and sometimes thousands of thermocouples that are wired in such a way as to produce a voltage that is proportional to the temperature difference. So instead of measuring an actual temperature across the wall, a voltage is generated that is proportional to the temperature difference, and it is proportional to the temperature difference of the average temperature throughout the wall structure itself. As a result, it's more accurate than simply measuring the temperature at a few places. The flow type calorimeter is somewhat different. It causes liquid to flow past the outside of or through pipes on the inside of the cell, carrying the heat out by warming the liquid that is flowing through this cooling channel. the cooling channel water is frequently used, and the temperature of the water entering the channel and leaving the channel is measured. Well, the methods for calculating the heat from these various techniques is fairly simple. In the isoparabolic techniques, the temperature difference is multiplied by a constant, which is the calibration constant that needs to be determined by experiment. And it's determined, I might add, by either placing a resistor in the cell through which a current flows, and the amount of power that is being generated within that resistor is then used to calibrate, or a dead cathode, one that does not produce any excess energy, is used, and the calibration is done by applying electrolytic current. In any case, one multiplies the temperature difference across the barrier times the calibration constant, which can be more complex than just simple number, I might add. From this is subtracted the amount of power going into the cell, which is the product of the voltage times the current. That difference is the excess power. In the Seebeck calorimeter, instead of a delta T, one uses the voltage that is proportional to delta T, multiply that times a constant, and then subtract the power that's going into the cell. The flow calorimeter calculates the power somewhat differently. The temperature change of the liquid is multiplied by the flow rate and by the heat capacity of the liquid. If all of the heat went into the liquid, then this would be an absolute type calorimeter that would not require calibration. However, very few are absolute, and so a small correction factor is found to be necessary. This type calorimeter typically has an uncertainty of about 50 milliwatts. The Seebeck is somewhat better. It has an uncertainty of perhaps 20 milliwatts. The isoparabolic calorimeter is, depending on whether it's single wall or double wall, the single wall, 100 milliwatts perhaps, if you're fairly careful. The double wall can be much better than this. There are two kinds of calorimeters, the open type and the closed. In the open type calorimeter, the gases that are produced by the electrolytic action are allowed to leave the calorimeter. This takes energy away from the calorimeter, and this energy must be calculated properly and applied to the equations to calculate the excess properly. On the other hand, many modern calorimeters use the closed method. That method uses a recombiner in the gas space above the electrolytic above the electrolyte, and this catalyst combines the deuterium and oxygen back into water that goes back into the cell. As a result, nothing leaves the cell, and so these corrections don't have to be made. Well, let's look at the many studies that have been reported about energy production. This is a histogram comparing the number of occasions when the amount of power along this axis was reported. And I might point out, this is the report from each individual study that gave the highest amount of power. Many studies got more than one sample to turn on, and this compares only the most energetic of the samples in the set that they report. Well, first of all, you can see that occasionally very large amounts of power have been reported. This is 200 watts, so this is about 180 watts. Here's 100 watts. This is an extraordinary amount of power, much in excess of what the error in the calorimeter would be. But as one goes to lower and lower power, it's seen more and more often. If we take this region here and amplify it, magnify it, we can see the detail now. Again, there are significant amounts of power being reported, down to a couple of watts. But most of the studies produce power even less than that. So you can immediately see that not only are large amounts of power produced, but a significant number of studies have been made that produce an amount of power that's well in excess of the error in the calorimeter being used. Well, let's look at some individual studies. Here's a recent result reported by a company in Israel. This is an electrolytic study using palladium as the cathode, heavy water as the electrolyte. For a period of time while the cathode material was being loaded or reacted with deuterium, no excess heat was found. And here it's a little bit of excess heat was seen. The power was increased, but not in excess of 1 watt. So we're looking at a very small amount of input power. But at the same time, the amount of excess power on this axis increased dramatically, reaching an amount of 34 watts. This is rather erratic and unstable power that's being produced, but nevertheless it is significantly in excess of the error in the calorimeter. The company uses an interesting technique. They apply what they call a super wave. This is a high frequency complex voltage that's applied to the current passing through the cell. And this is found to have a desirable effect on the heat production. Well, these graphs show a different kind of effect that's discovered by Arata and Zhang in Japan. They place in a tube of palladium black, which is very finely divided palladium that has been pre-tested. And this palladium black is sealed in the palladium tube. The tube is placed in an electrolytic cell containing heavy water. A current is passed so that the heavy water decomposes on the palladium tube, which is the cathode, and gradually the deuterium diffuses through the wall and builds up a pressure of very pure deuterium gas within the tube that surrounds the palladium black. And you'll notice that for a significant length of time, nothing happened as this pressure built up. But then the excess power began to increase and then increase rather dramatically to as much as 24 watts of excess power. This is much in excess of the error of the calorimeter. If the sample is electrolyzed in light water, this effect does not happen. So you can see that simply exposing an active material to pressurized deuterium is sufficient to generate excess power. And I might add, helium and some tritium has also been found to be produced by this reaction. Well, in addition to many individual examples that I don't have time to show, there are also a number of patterns that we can look at. The deuterium to palladium ratio turns out to be very important. Everyone who makes the measurement finds out that this ratio has a big effect on heat production, and I'll show some examples. If one uses a electrolytic cell, the applied current also changes the amount of heat production. People have found out that the batch of palladium is also very important. If one's lucky to obtain a batch of palladium that's active, then most pieces within that batch will produce excess power. On the other hand, if you're unlucky, which is most of the time, the batch, none of the pieces within that batch will produce excess energy. There's also an effect of temperature. The higher the temperature, the more heat's produced. That's been found in ordinary D2O electrolytic action, but also in fused salt, which I'll show you. The effect of electrolysis time is important. It takes a while for the proper conditions to be created to generate excess energy. And that electrolysis time is a critical aspect of this phenomena that many people have ignored in the past. And finally, palladium, when it takes up deuterium, cracks. These cracks make it very difficult, or prevent, the palladium from achieving the high deuterium to palladium ratio. When people have now found ways of treating palladium so that it does not crack, the success rate has improved dramatically. Well, here's an example of the effect of the deuterium to palladium ratio provided by McCubry at SRI. You can see that when the composition, the D to PD ratio, was relatively small, the excess energy was very small. But as the composition increased, the power increased to as much as 6 watts. Not all samples are capable of getting to as high as 0.98, and so one would never get this amount of heat. But if a sample is capable of achieving that high composition, all studies show this relationship between the D to PD ratio and the amount of excess power. Here's another example provided by McCubry. When material that could only get up to 0.9 was measured, 17 of the samples that were studied produced no heat. When material was found that could go from 0.9 to 0.95, 9 of the samples produced no heat, but 6 did produce heat. And finally, when the rare samples that can get to 0.95 and as high as 1.05 were studied, all 15 of these samples made heat. Well, when a sample that's able to make excess energy is used in an electrolytic cell, this very characteristic behavior is found, that at low applied current, this is being the current density, no heat is produced until a very critical current density is reached. And only then is the excess power, shown on this axis, does it increase. When the experiment is run in light water, this effect is not seen. Here's another example of this effect that compares a variety of samples. Well, first of all, notice that none of the samples show excess energy unless there is unless a critical current is applied. But once it's applied, the excess energy now rises at different rates. Well, this is caused because these samples have different areas, different shapes, and different amounts of the nuclear active material on their surface. But nevertheless, regardless of these conditions, this critical onset is always seen. Here's another comparison of a variety of samples. This time it's the logarithm of the excess power against the current density. And notice again we have this very low amount of power at low current densities with an increase as the current density is increased. But all of the data appear to lie below a critical upper limit. In recent years, a few samples have fallen above this limit, but nevertheless there does seem to be an upper limit that can be achieved in these cells, which is heavy water at near room temperature. On the other hand, this data were obtained at high temperature using fused salt. This allowed a temperature of about 450 degrees centigrade to be used and resulted in much more heat production than was achieved near room temperature. People have run these electrolytic cells using heavy water near the boiling point, and they, at the boiling point, result in higher energy also. If heat is produced by a nuclear reaction, then we should see nuclear product. In the case of cold fusion, the nuclear product is helium. Here we are plotting the atoms of helium divided by watt-seconds, or the amount of energy, against the excess power produced by each sample. This dashed line shows the amount of power that would be produced by a fusion reaction, that is 24 MeV per atom. Well, notice that the data fall in a region about 50% below this. In other words, half the energy is missing. This occurs because the helium was measured only in the gas. Any helium that remained within the palladium would not be measured. So this is exactly what you'd expect if a nuclear reaction took place on the surface of the palladium. Half of the energetic helium would go into the liquid and then into the gas where it would be collected, and the other half would go the opposite direction into the palladium where it would be captured and not measured. There are two studies compared here. The original study by Miles shown by the open points, and then later another study was done by Bush at SRI using a Seebeck calorimeter. And notice that their data fall very nicely on top of the Miles data. So here we have an example of reproducibility. Well, here's another example of the relationship between helium production and heat production. In this case, the sample being studied is an ordinary chemical catalyst, which consists of palladium, finely divided palladium, deposited on charcoal. This was heated in deuterium gas for a period of time, and after a while the helium content of the gas began to rise, and the amount of energy generated by this process also began to increase. The energy is plotted here, and the amount of helium is plotted here. And you can see that these two independent measurements, the helium and the heat, track each other beautifully, going up to 160 kilojoules total energy. Notice that once the amount of helium rose above about 5 parts per million, the gas content had exceeded the content in air, and therefore these samples taken at the higher concentration of helium could not have resulted from an air leak. And the heat production was measured two different ways with good internal agreement. So here again is another clear example of a relationship between helium production and heat production. In addition to helium, tritium is also produced occasionally, but not associated with heat production and not at very high levels, but nevertheless at levels that should not occur under these rather benign conditions. Here's a study done at Texas A&M. On this axis we see the concentration of tritium, and on this the time. First of all, notice that no tritium was produced initially until the current was increased, and then tritium production started. When the current was increased again, the tritium production rate increased. It was very interesting. This was a rather unique experiment because finely divided dendrites were found on the cathode surface. And when this cell was shaken, tritium production stopped, and it did not resume until these dendrites had reformed. Notice also a cell run at the same time that was not active but was subjected to the same conditions showed no increase in tritium. Tritium can also be made by gas discharge. In this study, Tom Claytor at the Los Alamos National Laboratory caused a discharge to form between two palladium electrodes in deuterium. The gas was circulated within the apparatus, and the tritium was detected using the a device that was sensitive to the beta decay, the current generated by the beta decay. This technique was checked against the more conventional method by converting the deuterium to heavy water and then placing it in a scintillation detector. The two gave exactly the same values for tritium, and so you can be confident that these measurements are accurate. So you can see that for a period of time nothing happened. No tritium, excess tritium was generated. And then when the current was increased, tritium began to accumulate. And again, when the current was increased, it accumulated more rapidly. Again, it was increased, and it again went, the rate went up. And finally, the current was turned off, and the tritium content remained constant. Because this study was done using internal funding at Los Alamos, and because it was controversial, it was subjected to rather intense peer review. The laboratory invited scientists from all over the United States, from universities and from national laboratories, to come to Los Alamos, and for a day they would quiz Claytor about the details of his experiment. And each time this was done, the group came away agreeing that this was good work, it showed an unusual phenomena, and the work should continue. Well, the work did continue at Los Alamos for a while until the DOE brought it to a halt. The work is now being done at a private laboratory outside of Los Alamos. Because this study was done using internal funding at Los Alamos, and because it was controversial, it was subjected to rather intense peer review. The laboratory invited scientists from all over the United States, from universities and from national laboratories, to come to Los Alamos, and for a day they would quiz Claytor about the details of his experiment. And each time this was done, the group came away agreeing that this was good work, it showed an unusual phenomena, and the work should continue. Well, the work did continue at Los Alamos for a while until the DOE brought it to a halt. The work is now being done at a private laboratory outside of Los Alamos. Besides the production of helium and tritium, other nuclear reactions are found to occur in the cold fusion environment. And in electrolytic cells containing palladium cathodes and platinum anodes, other elements are found on the cathode that were not present before the experiment started. The most common of these elements reported are copper and zinc, with these other elements in less often reported. It would appear that the palladium, after taking up a proton or a deuteron, splits into two fragments which are these elements. If this split does not happen, then these elements might be formed as more deuterons or protons are taken up by the palladium. The problem is to explain something so heavy as lead. Well, an electrolytic cell, when the anode is platinum, platinum is transferred to and deposited on the palladium cathode surface. So platinum would be available to suffer the same kind of reaction that the palladium suffered. In other words, deuterons or protons would go into the platinum nucleus in sufficient number to build up to form these elements. This is an example of what is called transmutation, and it's an aspect of the process that is being seen more and more often as people look with more detail at the production of unlikely elements. Imamura in Japan at Mitsubishi Heavy Industries has been studying the transmutation reaction over the last several years, and as a result has gotten some very amazing results. I'll talk about this in more detail, but let's first look at the conclusions, look at what they found. They discovered that cesium can be made to take up 4 deuterons to form praseodymium. Strontium can be made to take up 4 deuterons to make molybdenum, and barium can be made to take up 6 deuterons to make samarium. These transmutation reactions have been examined a number of different ways using several different types of methods of analysis. And in addition to that, the work has been replicated in Italy and in Japan. Well, let's now examine how they go about getting these results. First of all, they take a piece of palladium and pass deuterium through it. Deuterium being on one side and the vacuum on the other, so that deuterium is caused to diffuse through the palladium. Now, the palladium contains a number of layers on the front surface that consist of alternating layers of palladium and calcium oxide. And these layers alternate in this region, and then finally there's a calcium oxide and a thicker layer of palladium. On this surface is deposited the target element. It can be cesium, it can be strontium, or it can be barium. And then it's simply exposed to the diffusion of gas. Well, here's the result of the diffusion. They analyzed the surface using X-rays, and this is the concentration in 2 separate samples of cerium, and this is the concentration of the expected product, praseodymium. And you notice over time the praseodymium concentration increases and the cesium concentration decreases on the surface. They find that the conversion rate of cesium to praseodymium is proportional to the amount of gas that has passed through the sandwich. And there's a linear relationship between the two. You notice that there's quite a bit of scatter when you look at the material that's been electrochemically added to the surface, but when ion implantation was used, the scatter is much reduced, but the same effect is seen. A sample of this palladium after the conversion process is then looked at with a X-ray beam that has a very small cross-section of only 100 microns. And you can see the detail that they get in analyzing for the praseodymium using this technique. Well, the amazing thing is that they see the praseodymium only in certain spots on the surface. In other words, the entire surface, most of the surface is inert. There's no reaction whatsoever, and the praseodymium is being converted only in certain regions. This means that these regions must be rather novel and unusual compared to the general surface. This kind of behavior, that is localized reaction, has been seen using the other techniques as well. Well, the use of barium provides another evidence for this reaction. Barium has a major isotope at 138 and a number of lesser isotopes at lower mass. When the barium takes up 6 deuterons to make samarium, that mass distribution is carried over into the samarium, so that samarium 150 now is greatly enhanced, where it's not a very it's not very highly concentrated in ordinary samarium. Well, this wasn't sufficient proof, so they used barium 137 enriched. And here you see the original material enriched in 137, and when it has taken up 6 deuterons to make samarium, it's now the samarium 149 that is enhanced. So you can see that the isotopic distribution of barium is carried over into the nuclear product. There's no nuclear product between barium and samarium. In other words, the deuterons go in as a unit in each case. I think we can now see why the LENR is so hard to replicate. The active material is present only in very small regions. The active material is a complex alloy with an unknown structure and composition, so you don't know what to look for. And you don't know where to look. And the active material rarely forms. It's generally formed by nature if she's in a good mood. And it's very difficult to make it form on purpose. The challenge, therefore, is to make the alloy on purpose and in large amounts, so that the phenomena can be made to replicate whenever you wish. And you need to take several things into account. We know that the nuclear reactions involve 1, 2, 4, and 6 deuterons that add to a variety of nuclei. The nuclear reactions involve both hydrogen and deuterium, but of course these result in different nuclear products. The nuclear reactions occur only in special solid environments, which I call the nuclear active environment, the NAE. The nuclear reactions produce little, if any, radiation or energetic particles that are detected outside of the apparatus. However, if the right detectors are used, these radiations can be discovered inside the apparatus. Significant radiation is detected inside, along with the other nuclear products. The nuclear reactions can occur at rates that make significant heat energy. Of course, they can occur at lower rates where heat energy cannot be detected. Nevertheless, the nuclear reactions can be seen at these levels. And the nuclear reactions can be initiated many different ways. It's been quite a challenge to try to explain these behaviors. At least 500 papers have been published containing various theories and variations thereof. And it would not be practical to examine each one. Most are either inadequate, wrong, or not very useful. I would like to list those things that I think a theory should address. Hopefully this will help in the future. The nuclear charge of the deuteron or proton must be lowered, but not by neutron formation. Neutrons produce nuclear products that are generally radioactive, and these are not seen, and they also produce radiation, which is not seen. The deuterons must form a cluster of 2, 4, or 6 deuterons after this lowering process has occurred. Even the fusion reaction, making helium, is thought to result from 4 deuterons getting together to make beryllium-8, and then this decomposes into 2 alpha particles, thus eliminating the need for the gamma radiation. The reactions must produce very little gamma radiations and few radioactive products. The process must occur spontaneously without significant energy being applied. It happens at room temperature without any effort once the nuclear reactive environment has formed, but it is helped by the addition of more energy, either as greater heat or energy in bombardment or laser light. The mechanism must occur only under very special conditions in unique solids. Otherwise, it would not be so difficult to reproduce. Well, I would like to suggest several general conclusions. The LENR phenomena is real and has the potential to be an ideal energy source. Significant energy can be produced using several methods with simple devices, such that heat that's generated could be available in individual homes. The effect requires use of a special solid material, the nuclear reactive environment, which needs to be identified and manufactured in large amounts. Well, I've only been able to tell you a small fraction of what is known about cold fusion. If you have other questions or are interested in pursuing the subject further, I invite you to look at these 2 sources of information.